Magnetic flux is similar in concept to electric flux. So given an area A with an area vector A being perpendicular to the area, and given a magnetic field B going through that area, then a magnetic flux through the area is defined as a dot product between a magnetic field and the area vector, and denoted phi b. So as we've mentioned before, if this were a closed surface, then the total magnetic flux through a closed surface is zero, because magnetic fields form closed loops. But for an open surface, this is not zero. And the standard international unit for magnetic flux is Tesla meter squared, or Weber, which is WB. So if we write this using the definition of the dot product being the magnitude of B by the magnitude of the area vector being the area of the surface by cosine of the angle between the two vectors, well, in this case the angle between the two vectors is 0, so the magnetic flux through that area is a maximum. And in this second case, where the surface is tilted by some angle, then a magnetic flux through this area gets reduced, and this can be seen if you resolve the magnetic field vector into components that are perpendicular and parallel to that area. So only the perpendicular component to the area contributes a magnetic flux. And if we keep rotating the surface anti-clockwise, so the area vector in this case points upwards, then the angle between the two vectors is 90 degrees, so the magnetic flux through this surface is 0. And in this case we'll keep rotating the area anti-clockwise, so the area vector points in this direction, and therefore you get an obtuse angle between the two vectors. So in this case, the magnetic flux is less than 0, or negative. And note that if we have a closed surface, then the area vector is perpendicular to the plane of the surface and always pointing outwards from the closed surface. Now if the magnetic field varies with the area, then the magnetic flux is then defined as the integral of the dot product between a magnetic field and a differential area vector. So for example, if we look at this circle from the y-axis, the magnetic field vectors are going to point out of the screen. So considering this circle has some radius r, and if the strength of the magnetic field varies linearly with the radial distance from the center of that area, so for example it's some constant multiplied by r, then we can take a differential ring of area that looks something like this at some distance r from the center and an infinitesimal thickness dr, then this flux integral becomes b naught r being the magnitude of the magnetic field by the magnitude of the differential area vector, which is the area of that ring, being 2 pi r dr, cosine theta. So the area vector and the magnetic field vector point out of the plane in this case, in the y direction. So cosine of the angle between them, being 0, gives 1. And then we integrate from 0 to the radius of that area. And that gives the magnetic flux. So if you evaluate this integral, you're going to get 2 pi b naught as constants. And the integral evaluates to r cubed on 3, evaluated at 0 and r. So what we get is r cubed on 3.